Last month, I gave a coding agent one job: fix the authentication redirect of an app after a token expires. And whatever you do, don't touch the public API. It said yes. It read the files, ran the tests, walked me through the plan. 40 minutes later, the bug was gone. So was the API I'd told it to leave alone. Here's the part I was stuck on. That instruction never disappeared. I can scroll up right now and point at the exact line. Keep the public API stable. It was right there the whole time. So this isn't a matter about an agent forgetting something. The rule was visible. The agent just stopped listening to it. Well, that day specifically, I really wanted to know why. Most of us picture this the wrong way. We imagine the agent sitting there reading the whole conversation top to bottom, the way you'd reread a long Slack thread before replying. That's not what's actually happening. Every time the agent takes a step, something behind the scenes builds a fresh packet of text and hands it to the model. Well, first there is your task, then some of the files it opened, the last few test results, maybe a summary of what happened earlier or something it pulled back from memory. Then eventually your current request goes on top, and finally the model answers from that packet, and only that packet. Technically speaking, there are really two different things we keep calling by the same word. There's context, that is, what the model can actually see in this one step, and there's memory, which is whatever the system stashed somewhere else and might choose to bring back later. The transcript you're scrolling through isn't the thing the model reasons over. That is actually the packet, and that packet gets rebuilt from scratch on every single turn. Once you see that, the forgetting the instruction bug starts to make a lot more sense. I know that such a behavior can occur to the best of us, and it is really annoying when you least want it to happen. But let me illustrate where that behavior is coming from and what that packet looks like by the time you're 10 steps in that thread. A chat is mostly you and the model talking. An agent does things. It opens files, runs commands, fails a test, and dumps 40 lines of red into the thread. It forms a theory and writes that down. You correct it. It writes the correction down too, right next to the half-abandoned theory. Every action leaves residue, and none of it gets cleaned up on its own. So the packet that started as a clean instruction slowly turns into something closer to an event log, a pile of everything that's happened, with no strong signal about what still matters. This makes it that your one real constraint, keep the public API stable, is still in there. It's just one quiet line now in a room full of louder, fresher noise. It didn't get deleted, it got buried. And to the model, a buried instruction and a deleted instruction produce the same result. Okay, you see, the obvious fix is to make the room bigger. Models now advertise context windows in the hundreds of thousands of tokens, some around 1 million. 1 million for Opus and the most recent state-of-the-art LLM models. So just give it more space and stop burying things, right? Well, unfortunately, that still does not properly fix it. A bigger room doesn't organize the room. It just means more can pile up before anything spills. And this is where the research gets genuinely surprising. You've probably heard that models lose track of things buried in the middle of a long input. That one's been known for a while, but there's a sharper finding that gets far less airtime. Take guessing out of it completely. Hand the model the exact passage it needs and guarantee the answer is sitting right there. You'd think that settles it. It doesn't. Just padding more text around that passage still makes the model's answers worse. So this isn't the model failing to find the information. It is actually right there, correct and findable, and the length on its own makes the model use it worse. But there's a weirder wrinkle underneath, something called attention sinks. The model pours a big chunk of its focus onto the first few tokens, almost no matter what they say. So put boilerplate at the top and your real instruction halfway down, and the boilerplate can actually win the attention just for getting there first. Position is not neutral. Where something sits in the packet changes how much the model weighs it, and that plays out at 2 levels. The first prompt you give an agent quietly ends up mattering more than the 10th. It sets the entire frame, and everything after it gets read through that frame. But it is not only which prompt comes first. Even inside one prompt, the lines up top tend to hit harder than the stuff you tack on at the end. Now, from a more common unit of measurement that we are all familiar to, where do tokens fit into all this? As you know, under the context window, under the position, the thing the model is really counting is not words and it is not characters. It is tokens. And once you actually look at how the tokens get counted in your context window, they become a lot more interesting than you'd expect. Start small. Take one line from our auth job. Keep the public API stable. In English, that's 6 tokens. Write the exact same instruction in French, and it's 9. In Chinese, 10, even though on screen, the Chinese is barely half the length. Same meaning every time. The model just charges you a different amount for it, depending on the language you happened to write it in. Now, scale that up to something real. Say you brain dump a whole feature idea to the agent, or just give an average prompt. Think about something around 70 words, for example, the kind of thing you'd type out without thinking twice. In English, that's about 90 tokens. But that's English. The same text in French runs over 140 tokens. Well, the more sequence of prompts you have, the more this becomes in the thousands, as you can guess. You can think that French is a bit more verbose than English. It takes more words to say the same thing. In Chinese, it is roughly the same as the French in number of tokens, even though Chinese, visually, is less than half as long on the screen. It is obviously less text in front of your eyes and still around 60% more tokens than the English. The language is definitely not the only factor for how much tokens you eat of your context window. It is also the tokenizer version, which is the particular way each model chops text into tokens. A well-known AI researcher ran the numbers across the major models and posted the benchmark, and the pattern is clear. That non-English tax depends almost entirely on who built the tokenizer. On the big Chinese models, that same Chinese text actually comes out cheaper than English. Google's Gemini and Alibaba's Qwen charge the least tax on other languages. Claude charges the most, by a wide margin. Same meaning, wildly different bill. And it's the tokenizer, not just the language, that decides the price. Now, scale up from one prompt and think about what your agent is actually holding at once. A system prompt, a rules file, your CLAUDE.md, your skills, maybe your project conventions or the reference documents you told it to read. Maybe it's also holding some screens of tool outputs or some memory file. The configurations are many, but the outcome is the same. Each of those is easily hundreds, sometimes thousands of tokens, and they're all in the packet together, all priced in these tokens that run fatter than they look. Every piece feels small when you add it. Every piece is quietly spending from the same budget. Stack enough of them up, a bloated rules file here, an inefficient tokenizer there, and you push out the one instruction that actually mattered, long before you ever hit the model's real limit. That is only just one agent. Imagine a multi-agent system, few of those on one job, passing work back and forth, all spending from the same budget at once. That's actually one of our future videos. Subscribe if you want to see it as it comes out. But regardless, at that setup of multiple agents, the outcome of inefficiency gets another order of magnitude. So, a couple of quick things to know. Newer models almost always come with a better tokenizer than the older ones. And even on the same model, the language you use changes two things: how many tokens you spend and how well it follows you. But here's our takeaway at this level of the video. Every time you hit send, your request gets packed into that packet we talked about, and that packet is measured in tokens, not words. How many? That depends on the language, the tokenizer, and everything already crammed in there with it. So your one instruction is fighting for space, and the more crowded it gets, the easier it is to lose the thing that actually mattered. Okay, so once you know you're on a budget, you start writing differently. And people have worked out a bunch of tricks for this. None of it's in the docs, it just gets passed around in threads and discords. The simplest trick to optimize the number of tokens and optimize your instructions, people call the caveman style. You strip the instruction down to the bone. Instead of, could you please investigate the authentication issue and preserve the public API where possible, you write, fix auth, keep API, small diff, run tests, if stuck, stop. Fewer tokens, sure, but that's not the real win. The real win is there's nothing soft left to negotiate with. A polite, padded instruction gives the model room to wriggle out. A blunt one doesn't. A cleaner move is to stop writing prose to the machine at all. Hand it structure, a small block of fields, or a schema instead of a paragraph. And the most underrated one, don't put the big thing in the packet at all. Drop whatever you have as requirements and constraints in a separate file and pass a pointer to it. Just let the agent carry the address, not the cargo. You see, all of this makes even more sense when there's no human reading at all. When one agent hands a job to a sub-agent or one agent to another, nobody in that chain is impressed by a polished sentence. The niceties are just wasted tokens. That's why you're seeing the caveman style, or the variation of it called Chinese grandpa style, spread as more of the work moves agent to agent, and the compression gets to go even harder for the internal communications. They're all the same instinct from different angles. Every token in the packet is competing with your actual instruction, so spend them like they're scarce, because they are. Okay, so here's the thing. All of what we just discussed is you, doing it by hand. You can only hand compress so much. The system compresses too, on its own, behind your back, and that's the part that bites. Every serious agent does it. Claude Code, Cursor, Gemini CLI, and the other open source agentic systems. Same wall, same fix. When the history gets long, summarize the old stuff and keep going. But summarizing sounds harmless until you look at what a summary actually drops. This is called compaction, and it has to happen. You can't just carry every log line forever, but every summary loses something. So watch what it does to that authentication job from earlier. The real history said two things. We think it's the cookie path, but we're not sure yet. And whatever you do, don't touch the public API. The summary that replaces it just says, it's the cookie path, go fix it. Cleaner, shorter, and it quietly dropped the two things that mattered, that we were never sure, and the whole rule about the API. From that point on, the agent isn't working on my task anymore. It's working on the summary's version of my task. And the summary doesn't even know the constraint was ever there. The agent didn't change the API because it forgot. It didn't miss the rule either. It changed it because somewhere in a routine compaction, that rule stopped being part of the state. And here's the part that should worry you. This doesn't happen once. Keep the run going, and the system compacts again. And in a lot of setups, that first summary gets summarized again with the new residue. A summary of a summary, each pass thinner than the last, with nothing left to rebuild the original from. Whatever barely survived the first round, shrunk, softened, the next round can just finish off. Now, compaction is the best hack we have. Every serious agentic harness uses it automatically to keep a long run inside the context window, and you can't really switch it off. So the question isn't how to avoid it, it's what you can actually do about it. The fix isn't only a better prompt, it's also refusing to let the transcript be your memory. You keep a small working state right beside the run, a few lines you control, and you treat that as the truth, not the chat. Well, for me, it's 5 fields. 1. The contract. The rules that aren't allowed to drift, like don't touch the public API. 2. The evidence. The failing test, the exact log line, what you actually know right now. 3. The open risks. The cookie path is still just a theory, not a fact. 4. The next action. One step, like inspect a branch and run the tests. 5. The reset rule. If a test kills the theory, stop and write down where you really are instead of digging in deeper. This, eventually, also changes where you keep the things that matter. Here's the difference. A prompt becomes a line in the conversation history, the exact thing that gets compacted. Say, don't touch the public API at turn 1, and by turn 25 it is just buried under the residue, or even summarized away. On the other hand, luckily, a rule or a guideline file usually lives in a pinned layer that the agent's harness reinjects, and that the compaction itself does not change. It comes back fresh. It doesn't ride along in the part that gets compressed. It is not magic. Eventually, a bloated rules file still spends from the same token budget, and the careless system can let it decay. But, the thing you can't afford to lose should belongs in the layer that gets reread, not the layer that gets summarized away. So, okay, the real move is to get ahead of it. Compress on your own terms before the system does it for you. However, that needs the one thing you usually cannot see. You need to monitor how full your context window actually is at any given time. Most of the time that number is hidden. You've got no idea you're at 80% of your context window until the thing compacts and your run quietly goes dumb. There are a few ways to see it. The basic approach is that you can use a slash command like /context to check where you are. Or you can actually run a plugin that brings your live overview of your context window spending. If you do not have a native plugin by default in your agentic system, there's a one called CLAUDE Context Monitor. You can also format it to be used for other agents as well. But in a nutshell, it puts a live meter right in front of you. How full the window is, and roughly how many turns you've got left. Although really, you want to keep that context window under 50% for the best focus and performance. A plugin like this can nudge you at 70 or 80%. But honestly, a nudge at 70 is already a bit late. A lot of builders refresh around half, because half a window of clean, focused state beats a full one that's 3 summaries deep. This is not just a Claude code hack. Every agent hits the same window and the same wall. So when you refresh, you don't start from nothing. You ask your agent for a handoff first. Something as simple as, I want to start a new session with a fresh context window. Write me a handoff message I can paste into a new session to pick this up from where we left off. Include the contract we can't break, what we actually know right now, the open risks, the next action, and the reset rule. This get you your 5 fields back, clean. Start a fresh session, paste it in, and you're holding a full window of only what matters. So now, let's quickly go back to that agent that changed my API. It wasn't dumb, and it didn't forget. It just got handed a packet where the one rule that mattered had been compressed down into background noise, and it simply answered the packet it was given. That is all what these models ever do. This is not even about good prompting. This leaves one rule I'd tattoo on a coding agent if I could. Stop managing agents by how long the conversation is. Manage them by how clean the working state is. The best run isn't the agentic flow where the model remembered everything. It is the one where, on every single step, the thing that mattered was still the loudest thing in the room. I hope this gives the right pointers to better agentic builders. This is pretty much it for now. Subscribe for more deep dives and comment a topic you want me to cover in the future. Check me on the next one. Peace.